Welcome, Algebra 3, to Lesson 15, the lesson you've all been waiting for, where we dig deeper and start writing proofs, some serious proofs, not just using one of the four congruency for triangles, but actual proofs. So remember that definitions are the names we give to ideas or things, and that all definitions are reversible. We can also use definitions within our proofs. That's something that you need to make a note of. So, for instance, if we have a midpoint or a bisector as in a figure, we can use that. We can say the definition of a midpoint. Instead of having to write the definition out or logic out why it's the same, we just write the definition. Or we just write that it is in the definition, right? A reference point. We make a distinction between the meanings of words axiom and postulates. We say that an axiom is an assumption that is true in all areas of mathematics, right? And a postulate is an assumption that is applicable to just a particular branch of mathematics, in this case, geometry. So the first recorded postulates are the geometric postulates of the Greek scholar Euclides, who we now call Euclid. And he probably lived in Alexandria, Egypt, during the reign of the first Greek king of Egypt, Ptolemy I, around 300 BC. Not that, this is not a history lesson. That's not my thing. It's just, interesting facts. So let's go over his first 10 postulates, or the 10 postulates that he narrowed down to be the most important for us to learn. I'm going to write them on here, and then we'll talk about each one, okay? So let me pause this. Our first postulate is 2 points determine a unique straight line. Pretty straightforward stuff. If you have a point here and a point here, any 2 points, regardless of where, they're going to make a unique straight line. If I do 2 points here and here, that's a unique straight line. Any 2 points that I draw creates a straight line in reality, right? So those are all just, you can do a straight line between any 2 points, is all we're saying. That's pretty straightforward. So let's look at the next one. Oops. There we go. Postulate 2 says that a straight line extends indefinitely in either direction. So it's something that we illustrate by using the little arrows on each end of the line that, if left unchecked, they would just keep going as if they had a mind of their own. It signifies that there is, as far as we know, unlimited space, and if we imagine a line in space, it's going to continue in either direction until something stops it. Who knows? So let's look at that third postulate. Postulate 3 says that a circle may be drawn with any given center and any given radius. And, that's just saying that you give us a point here in the middle and you designate a distance from that point. You can draw measuring all the way around in any direction whatsoever. As long as it's the same distance all the way around, it's going to create a collection of points that's going to form a perfect circle. Now, you wouldn't think you'd have to spell out postulate 4, but he did it anyway. Postulate 4 says all right angles are equal. So, that's the very definition of a right angle, right? That it is a perpendicular line. Therefore, it quarters a circle. So, every right angle is 90 degrees. And we can get 4 equal right angles out of the center of a circle. That's just the very definition of a right angle. So, of course, all right angles are going to be equal. In postulate 5, we are told, given a line N, so here's line N, and a point P, not on that line, so I'm just going to make a point here. This is P. There exists in the plane of P and N through P only one and only one line M, which does not meet the given line. So here, which does meet the given line N, that by definition is a parallel line. So if you're given line N and another point that's not on that line, there can only be one line through that point that is parallel to N. That is what this postulate says. So I can only draw one parallel line that goes through P that is parallel to N. That's it. That's all that whole thing says. In postulates 6, 7, and 8, there's some basic axioms here. Things equal to the same thing are equal to each other. And that is very similar to what we call the substitutive property. So that is where we say if A is equal to B, actually no, this is more transitive, where if A is equal to B and B is equal to C, then A is equal to C also. That's very much like the transitive property, where if things are all equal, then they're equal to each other. If they're equal to the same thing, if A is equal to B and C is equal to B, then A must be equal to C. So let's put a little parenthesis out here. This is the transitive property, if I can write today. So this is the like the transitive property, right? Number 7, postulate 7 says if equals be added to equals, the sums are equal. Makes sense, right? So if I have, let's say, I have 3 and 3, and to this 3 I'm going to add 4, and to this 3 I'm going to add 2 squared. Well, this is 7, and this is 7. These are equal values added to equal values, so their sums are equal values. Same thing for subtraction. 7 minus 4 is equal to 3. 7 minus 2 squared is equal to 3, because we have the same number, subtracting the same value, giving the same remainder. So that's all postulate 7 and 8 is all about. So it works with postulate 6, which is why I put all 3 of them up there at the same time, so you can see how those tie in to one another. Okay, let's do the other 2, or the last 2. So postulate 9 tells us that figures which can be made to coincide are equal. And that just means that if we find enough congruency, or we're able to prove a congruency, or if we're able to lay one on top of the other and show that they're equal in every way, then they're equal. Number 10 says the whole is greater than any part, which we know from working with algebra, from working with whole numbers and fractions. A whole number is greater than any fraction or decimal value of a number. And the whole of any shape is going to be greater than any part of any shape. So let's refresh our memory on our triangle congruency postulates. There's 4 of them. I'm going to write them right up here for us. Remember, we have side, 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 and these are triangle congruency axioms. You have side, side, side. So if you have 3 sides and 2 triangles or more, and all 3 sides in all of the triangles you're talking about have the same lengths, then those triangles are going to be congruent. Then you also have side, angle, side, where if you have 2 sides and 1 angle that are congruent, then those 2 triangles or more are going to be as congruent as well, because of the nature of triangles. When you have 2 sides that are the same, and then an angle between them that measures the same, then it has to be congruent. Then we also have angle, angle, side, which can also be written as angle, 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 side, because we know that if two angles in a triangle are congruent to one another, then that third angle is going to be congruent because of the nature of how triangles are made. And if all three of those angles are the same, and one of the sides matches one of these sides in the other triangle, then the other sides are going to line up as well, because they can't have the same angles if the sides are different lengths. Right? So the last one is hypotenuse leg. And really and truly, hypotenuse leg is just another version of SAS, because we know that hypotenuse leg is only relative to a right triangle, right? And if we have hypotenuse is the same, right? Let's say we have two triangles here. We have the hypotenuse is the same, and one of these legs is the same. We know this other angle is 90 degrees. So that's side, angle, side. Side, angle, side. So a hypotenuse leg is just side, angle, side, because it refers to a right angle. Why do we know that it refers to a right angle? Because only a right angle has a hypotenuse. So if the hypotenuse and one of the legs are the same, then we know it's side, angle, side. It's just another way to say it in reference to a right triangle. All right, so let's pause this. I'm going to clear the page. If you need to pause and take notes, do so. I'm going to put example problem 15.1 on the board. So here's our first practice problem. A median of a triangle is a segment that connects a vertex with the midpoint of the side opposite the vertex. So the median of a triangle, needs to line up and down here, is a segment that connects the vertex with the midpoint here on the side opposite the vertex. Prove the median drawn from the vertex formed by the equal sides of a sausage. Well, that just doesn't sound right, does it? Of an isosceles is what it's supposed to say. Let me highlight that. An isosceles. I should proofread more often, huh? Proof that the median drawn from the vertex formed by the equal sides of an isosceles triangle bisects the angle at this vertex. We get to prove that this is basically that the angles formed are congruent, that it bisects the vertex. So the way we're going to do this, instead of trying to do a paragraph proof, which is, a lot of words, we're just going to do statements and reasons, and we're going to list them. This is what's called a 2-column proof. Statements and reasons. And whenever you do a proof, this is what you're going to do. You're going to do your statements and reasons. And for every statement, there is a reason. So first, we have, the very first thing we have is that AB is congruent to BC. And this is the reason we know this is true is because it's given in, and then it's the definition of an isosceles triangle. We have two sides they're saying. Second thing that we know for sure is that we're going to have to draw a line from the vertex to the midpoint. So we're going to do that here. From here to here. And this is the midpoint here. And this midpoint, let's label it D so that we have that. Okay, so we are going to draw, we drew the median, so we're going to write draw median. BD to AC. That's what we did. And the reason for that is that it's given instructions. I can't really write today. My pen has been messing up on me, and so this looks really bad and wonky. I'm gonna try to write that better. It's given instructions. What we're supposed to do. And you could just write given right there also. That would work. So number 3, we are going to look at the rest of this shape. Because this is the midpoint, we know that AD is congruent to DC. So because of that, we can make that statement. AD is congruent to CD. And that is going to be the definition of midpoint. All right. So number 4, what we're going to do is we are going to circle this line in the center, BD. BD is the same leg in ABD as it is in CBD. BD is the same leg for both. It's being used. It's a shared leg, so to speak. So we can write BD is congruent to BD. And that is the reflexive property. Reflexive property just means that a thing equals itself. That's all the reflexive property is. Next, we're going to say that triangle ABD is congruent to triangle CBD. Notice how I have B in the middle of this vertex. It matters which one's first and which one's last. And that is going to be because of side, side, side. Because we've already said that AB and BC, there's one side. That's given to us with the tick marks because this is an isosceles triangle. And then we drew our median. And then that gave us AD and CD being congruent because this is a midpoint. So that's our second side. And then BD is a shared side, so it's the same for both. That's our third side. So therefore, triangle ABD is congruent to triangle CBD because of the side, side, side congruency postulate. So therefore, we can say that angle ABD is congruent right here to angle CBD, and that is because congruent parts of congruent triangles are congruent. Alrighty then, kind of see how that works out. Now, the problem with teaching proofs and the problem with grading proofs and the problem with putting proofs together is that there is a stream of consciousness, a thought process that goes behind it, and not everybody thinks the same way. This one is fairly straightforward, and most of us are going to draw the same conclusions in the right order because of the way the shape is made, right? So there's not a whole lot around that. But you're going to come across some shapes and some proofs that you have to write where you could go more than one direction to get to this. It's very similar to writing, and there's an objectivity there that is required. It's not just black or white. It's not the right answer or wrong answer. So when you do your proofs, what I'm going to be looking for are your statements and reasons, not necessarily in a specific order, but that the reasons, the statements lead from one to another, and the reasons back up your statements. So that is the point of a proof, is that you can think through from point A to point B in a logical progression, and that you can back up with reasons that make sense, that support your claims, so to speak. All right, so let's look at another one. We're going to skip 15.2 for right now. We'll go to 15.3 because this is one I think that you guys would enjoy. And actually, I think that we've done this one in class before, or I've mentioned it. We're going to prove that the sum of the measures of the angles of a triangle is 180. This is 15.3. So here we have a triangle, right? And we're going to prove that angle A, B, and C equals 180 degrees. All right, so in order to do that, I've got to think about how can I prove this? What other relationship or what other item that we know has 180 degrees that I can relate it to? Well, a straight angle has 180 degrees. So if I draw a line that is parallel to the base of the triangle, right? Then that kind of makes this side of the triangle here a transversal, and the base of the triangle is going to be a parallel line to this one here. So I have two transversals that intersect at the top parallel line, and they cross each other, and then I have another parallel line here. So that's forming my triangle with some transversals. So now I can relate some things here. So in this figure, we see that vertex B, we see that angle, let's call this, let me rewrite B out here. And I'm going to put C, actually C can stay in here. All right, I'm going to rename this 1, 2, and 3. All right, and the reason I'm going to do that is because this is supposed to be 180 degrees from here to here, right? Okay, so that means that angle B is equal to angle 2. So let's start with statements and reasons. All right, so I am going to first start with a given, triangle ABC. It's given. Always start with your given. Whatever you're given, you know, that's what you write first, so you can state your case. Number 2, I am going to say draw, let's say I draw a parallel line. Parallel to, let me rewrite that. Draw a straight angle parallel to AC. Okay, and we know that through a point not on a line, there's exactly one line parallel to the given line. This is the point not on this line. So that is going to be postulate 5. So postulate number 5, right? So now, this is where we are now. I'm going to say the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 equals 180. And my statement here is going to be a definition of straight angle. Right? Number 4, I'm going to say that angle 2 is equal to angle B. And that is going to be transitive. No, that's definition of vertical angles. because angle B, well, actually it's not the definition of vertical angles because it's the same angle. Angle B and angle 2 are the same. So that's reflexive property. Right? Because this is angle B right here. It's the same thing. I can actually just take that off now that I've got B right there. So that's a reflexive property. Angle 2 is angle B. Therefore, they equal one another. All right, so 5, let's say I can put the measure of angle 1 plus the measure of angle B plus the measure of angle 3 equals 180, and that's going to be the substitution property. Right? Number 6, I'm going to put the measure of angle 1 is equal to the measure of angle A, and the measure of angle 3 is equal to the measure of angle C. And that is going to be if two parallel lines are cut by a transversal, then each pair of alternate interior angles is equal, right? So this 1 is an alternate interior angle to A. So this one is congruent to this one. And then because of the same reason, we have an alternate interior angle here. This one is congruent to this one. So this is the definition of alternate interior angles. And you can just do angles like that. So because of that, I know all 3 of these angles equals 180 because this is a straight angle. So this one is this one. This is the same one, and this one is this one. And I know this is 180, so therefore all 3 of these is equal to 180. So I can say for number 7, the measure of angle A plus the measure of angle B plus the measure of angle C, if I can write it, is equal to 180. And that is going to be substitution as well. And that is my final statement. So you can see how we work that out. We talked about, first of all, that these two, we had to go with postulate 5 to back up drawing this parallel line here. Drawing that parallel line allowed us to substantiate something that we know equals 180 degrees because we know that a straight line bisects a circle and therefore measures half of a circle. So half of a circle is 360 divided by 2, that's 180 degrees. So a straight angle is 180 degrees. And then looking at alternate interior angles and their congruency, we were able to prove through substitution how that equals 180 degrees on the inside of a triangle, which is kind of cool. It's kind of neat how that works and how we can put all of that together. All right, so let's look at, let's see, do we want to do one more? I think I have 3 more. Let me look at my book. Yes, I have 3 more that we can do. I think let's just do 2 more. Let's do number 15.4. And here we have just 2 intersecting lines. And we have angle A, angle B, angle C, and angle D. We're going to use the 6th and the 8th postulate. The 6th and the 8th postulate to prove that vertical angles are equal in measure. So prove vertical angles are equal in measure. All right, so here's our statements. And here's our reasons. So statement 1, we might say angle A and angle C, angle A and angle C, are vertical. That's a given by the definition of a vertical angle. These two are vertical angles. 2, we could say that the measure of angle A and the measure of angle B are equal to 180 degrees. And that is going to be the definition of a straight angle. All right, number 3, we can say that the measure of angle B plus the measure of angle C is equal to 180. And that is also the definition of a straight angle. You see what I'm putting down here? So A plus B, that's a straight line. So A plus B has to equal 180. And B plus C is also a straight line. So B plus C also has to equal 180. So therefore, using, I think it's the 6th, yes, using the 6th one, let's do number 4. So the measure of angle A plus the measure of angle B is equal to the measure of angle B plus the measure of angle C. And that is going to be things equal to the same thing are equal to each other. They're both equal to 180, so they're equal to each other. So that is going to be postulate 6. Okay, so now we can actually solve that. We can subtract B, measure of angle B from both sides, and we're left with the measure of angle A is equal to the measure of angle C, and that's the 8th postulate, where it says if equals are subtracted from equals, the remainder is equal. So it's postulate 8. Remember when we went over that and we said 7 minus 4 is equal to 7 minus 2 squared, which is still 4. That was a hypothetical. Here we have, we've subtracted this from both sides, so these are remaining, and it's just saying that we've subtracted the same thing from both of these, so therefore if these are equal, then A and C have to be equal. So we have proven that vertical angles are equal in measure through this definition. Now you could have said angle A and D is equal to 180 and C and D is equal to 180. You could have said BC and DC. So you see there's a couple of different ways you could do it. You could attack it. But you're basically going to do the same thing. You're going to say these are straight angles, these are straight angles. And there is a commonality here that is B. So if you take B away from AB and you take B away from BC, and they're both equal, then A and C have to be equal as well. So that's how we're going to use our postulates whenever we do our statements and reasons. You don't have to write it out for me. You can just refer to the postulate number. I'm happy with that. So let's do one more. Let's do 15.6. And I have, let me say 15.6 here. I have a shape here that's not exactly a square. It's like a rhombus. And I have, these are parallel to each other, these two sides. And I have a diagonal from here to here. So I have Q, R, and P, S are my vertexes here. So the given that I have is that angle Q is congruent to angle S, and that PQ is parallel to RS, or SR, either way is right. Actually, it should be SR, because if you did PQ, you should do SR. You start from the same location. So now what we have to prove is that triangle PQR is congruent to triangle RSP. All right, so let's start with our statements, and then we'll write out our reasons. All right, so statement number 1, and we always start with a given. Angle Q is congruent to angle S, and that is a given. All right, we have 2 givens in this. The second one is that PQ is parallel to SP. Is that SP? SR, sorry. That should be SR. I don't know why I wrote P. And that one is given as well. All right, so now let's look number 3. If 2 parallel lines are cut by a transversal, then each pair of alternate interior angles is congruent. That's the definition of alternate interior angles. So what we're going to do is we're going to visualize that angle QRP, which is this one, QRP, it's congruent to angle SRP. So this one here is congruent to this one here because of R here. And we're going to use the alternate interior angles. Definition of alternate interior angles. Number 4, we have angle QRP is congruent to angle SPR. So QRP is congruent to SPR. So this angle is congruent to this angle. And that is also, if 2 angles in one triangle are congruent to 2 angles in the second, then the third angles are congruent. So that is two angles in one triangle are congruent. That's side, that's not side. That's angle, angle, side. Actually, I'm getting ahead of myself. 2 angles in one triangle are congruent to 2 angles in a second we're going to do angle, angle, angle. Angle, angle, angle. That's what that is. If two angles in one triangle are congruent to two angles in the second triangle, then the third angles are congruent. So it's angle, angle, angle. All right. 5 PR is congruent to PR. And that is the reflexive property, which just says that things are congruent to themselves. So number 6 would be triangle PQR is congruent to triangle RSP. And that is going to be angle, 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 side, because of number 5, they share the same side. Alrighty. Okay, I know this is all confusing, and it kind of takes a little bit of thought and a little bit of reasoning to kind of see what your next step is. I'm going quickly with these because all the answers are in the book. I mean, I don't have to pour my brain over them, but I want you to see by these examples kind of how the process works. And it's going to take you a little time when you first get started. Those first few proofs that you have to do, you're going to say to yourself, what's the next step? I don't know how to do the next step. Where am I going? One of the ways or the techniques that you might want to use is to think about what you have to prove and work yourself backwards. That's one of the things that you can do. If you can work yourself from what you need to prove back into what's given, then you'll be able to see what you need to see more accurately and do a better job of writing the proof. And by that I mean you're going to say, well, what I need now is for this to be, to identify that this is the same thing. So then you write that down, right? And then you go, okay, well, if that's the same thing, then you back it up. You keep until you get to what you are given to start with. So yes, start with what you're given and work to prove it, or to prove what you're asked to prove. But then, don't be afraid to look at what you have to prove and figure out which direction you have to go from what you're given. That's the whole point, is to get where you need to go, and looking at the direction of what has to be proven is going to give you that. That being said, it's not going to be super easy at first. It's going to take practice, just like all of the other math skills that you guys have honed. It's going to take a minute. All right? It's okay to ask for help on these. If you need to be walked through, or for someone to hold your hand, come to study group and let's talk about them. Let's sit down, or stay after class, or ask me in class. Okay, look, these proofs are kicking my hiney. How do I know what the next step is? And let's go through them together, because you have to see it in order to write a proof. There's more than one right answer. So you have to write down what you see to get to what you have to prove. And that's really all I have for lesson 15. I will see you in class. So bye for now. If you have questions, please message me.